Hello everybody and welcome back to Advanced Functions. Today we'll be doing chapter 3.3 of Rational Functions, which focuses on a new type of rational functions. I know, this is so surprising. Also, I realized I made a tiny mistake. I didn't change the number. So let's do that. So the new type of function we're learning has the following form. F of x is equals to ax plus b in the numerator divided by cx plus d in the denominator. Again, we'll be following the exact same steps we did in the last two chapters. We will first of all be analyzing the function, then learning how to graph it. However, this form has a special case, which we will be discussing last. So up first, of course, let's analyze the function. A rational function of the form f of x is equals to ax plus b divided by cx plus d has the following key features. The following asymptote can be found by setting the denominator to equal to 0 and solve for x. This is what we've been doing for all the rational functions we've learned so far, so that's nothing interesting, provided that the numerator doesn't have the same 0. This is a new point because the last ones we've been dealing with have only had whole numbers on top, right? But now we could have any type of 0 on the numerator. So if they do have the same 0, that means you will have a hole at the x value and not a vertical asymptote. The horizontal asymptote can be found by dividing each term in both the numerator and the denominator by x and investigating the behavior of the function as x approaches positive and negative infinity. So in case you're wondering why this works, it's essentially the exact same process we've been doing in the last couple of functions. However, here, since we have two x values, it's easier for us to try and make them into just constants rather than dealing with a equation, right? So if we divide everything by x, we would actually eliminate the need to think about the variable. And with that in mind, we could then find the horizontal asymptote. So if you need, I could do an example of how this works, but essentially what you're doing is we're saying that ax plus b divided by x would be a plus b over x, right? And cx plus d would be the same as c plus d over x. Then we're making x equals to positive or negative infinity, right? So the x value is either really, really small or really, really large. No matter the case, we have d divided by a really small or really big number, which would make it approach 0. As d approaches 0, the only things we have left is a and c, right? Therefore, what we finally find is that the vertical or the horizontal asymptote is equal to the value of a over c. Next, we could talk about the coefficients. We have one coefficient, which is b, which is in the numerator, and b acts as a stretch to the curve and has no effect in the asymptote's domain or the range. So again, it's just a stretch factor. And then the d factor, or the d coefficient, is just a shift to the vertical asymptote. Again, this makes sense considering the fact that's all we've learned about the denominator, how it helps us find the vertical asymptote. So if we start moving it left or right, the d coefficient has to come up somewhere. Lastly, we could also analyze the two branches that are formed from these types of functions. So what we know for sure is that the graph of the functions, the two branches are equidistant from the point of intersection of the vertical and the horizontal asymptotes. This is a really big point that you have to learn just because it makes your graphing life so much easier. Just remembering that they will be of an equal distance apart away from the vertical and horizontal asymptotes. Like, it just genuinely makes your life easier. Now, if you've looked at this, I would like to introduce you to a couple of other points that you may not have realized occur with these types of functions. So essentially, there's a little bit of a life hack for you to find all the key information for these types of functions, and that is just remembering these four equations. These four equations are of course derived from the actual form of the function, but essentially what you need to remember is that the horizontal asymptote is equals to the value of a over c. the vertical asymptote is equal to the value of negative d over c, the x-intercept is equal to the value of negative b over a, and the value of the y-intercept is equal to b over d. Over here, we'll provide a video on how these equations are actually found, but since we're doing a video, I will just show it to you in a moment. Okay, so using Desmos, I graphed the function ax plus b over cx plus d, where I let the constants equal any of these values. You could just click play and see how they change things. As you could see, as we said, the d just changes where the vertical asymptote occurs. C changes the, how to explain it? It's essentially just stretching it in a certain factor. Then B is again just pulling them further and closer apart. And then A does a really similar thing to C, which is not surprising considering they're the ones that are actually affecting the variable of x. So then over here, I graphed the information I just talked about. Let's first of all talk about the vertical and the horizontal asymptote. So as you see here, let's say let A flow. As A flows, we see that the horizontal asymptote moves with the graph, which means that our equation is correct. If you remember, I talked about this a couple moments ago. The way we could find the horizontal asymptote is again by dividing everything by x. So when we did that, again, we eliminated the b and d values. So we were left over with a over c, which is exactly what the function is equal to. That's how we found the horizontal asymptote. The vertical asymptote, again, we've learned about this a long time ago, way back when in chapter 3.1. And over here, all we have is the rewritten form of the denominator. So I just let this equal to 0, right? So then I move d to the other side, so we get cx is equals to negative d. And then I divided everything by c. So we got x is equals to negative d over c. As we see here, that is the equation we have. So again, let's run d, since that's the only coefficient, or actually let's run c. As you can see, again, the vertical asymptote follows the graph, therefore it was the correct equation. The x and y intercepts are a little bit more tricky, but again, not really. The y-intercept is kind of easy, because finally we have a variable at the top. So over here, we again said that let this equal to 0. So then ax is equals to negative b, or x is equals to negative b over a. So now what we got was negative b over a being our x-intercept. So again, let me rewrite this. And let's let the graph flow. Again, this line is following where the x-intercept is. So we're good in that plan. And lastly, we have our y-intercept. The y-intercept is a lot more fun, right? Because instead of making x equal to positive and negative infinity, we're making x equal to or approach 0 or equal to 0. When we get x equal to 0, the a and c factors just kind of get removed and all we're left with is b over d. Again, letting the graph run. Well, let's not do a, let's do b or d, because those are the factors actually affecting it. As you can see, the graph is following the y-intercept perfectly, and that is again how this works. If you want to memorize each of these graphs or these equations, you could easily do so, but again, just simply looking at the equation of the function, you could interpret them and derive them simply, so you don't have to necessarily memorize them, but they will make your life a whole lot easier. With that out the way, we can now move on to actually graphing the functions. So to graph the functions, we actually need to do the following thing. With that being out the way, we can now talk about actually graphing the function. So once you've acquired all the key information for each of the graphs or each of the functions you'll be working with, you could finally graph the function. This is actually really simple, as again we discussed all of the simple or the key information can be derived from these 4 equations. So using these 4 equations, we could first graph the vertical and horizontal asymptotes. Again, there they are, that's the values of them, so it's rather easy. Then you could plot the y and x intercepts. Again, we know how to figure those out, so it's not difficult. Now we just need to graph each branch. The key part with this is to remember how those branches will be behaving compared to your vertical asymptote, your horizontal asymptote, and your x and y intercepts. So what you could do is, of course, make an interval chart, like we've been doing in the last couple of lessons, where you could analyze the behavior of the graph depending on how it is behaving when it is approaching the asymptote, if it's increasing or decreasing, if it has a positive or negative slope, etc. But again, if you just remember the little detail we learned about in chapter 3.1 about how those graphs actually look like when they're positive and increasing or like negative increasing, you can make this process a whole lot faster. Just remember to talk to your teachers or listen to your teachers so that you know whether or not the interval chart is a method you have to follow or if it's just something that should help you out. Of course, when it comes to graphing the function, you could also go the other way around and someone might ask you to get the equation from the function that has already been graphed. So if this is the case, your life is still extremely easy because you are immediately given the equation for the vertical and horizontal asymptotes. Now you'll also be given the x and y intercept. So what you have to do is actually start substituting those values and solve for each of the 4 variables you don't know, which is a, b, c, and d. Personally, I like to start with the x-intercept and the vertical asymptote because those are dealing with the numerator and the denominator. So for example, if your vertical asymptote is at x is equals to 1, that means your denominator should be of some form of x minus 1. Then, with that in mind, you found your a value and your your c and d value. With those, you can now find your horizontal asymptote, for example. Let's say it's 2. So we know that a over c is equals to 2, and we know that c is equals to 1, therefore a has to equal to 2. So now we only have one last variable left, which is b, and if our x-intercept was something along the lines of, let's say, 4, we know that 2x plus b is equals to 4, so now we just know that x is equals to, sorry, that was wrong. So we know that 2 times 4 plus b is equals to 0, since that's the y value when we have an x-intercept. You simply say that 2 times 4 is 8, so 8 plus b is equals to 0, so b is negative 8. Now that you found all of your key variables, you could write them into the equation and get your form. That's all you have to do. Again, it's a little bit complicated when I just simply tell you what to do, so I will demonstrate both of these concepts on an actual, by actually writing them on the next slide. So the 2 examples we'll be following is graphing this function over here, which is 2x plus 7 divided by 4x minus 1, and also trying to find the equation for the following graph. Okay, so I wrote the question down and now let's actually try and solve it. So at first what we should do is figure out the a, b, c, and d values for this particular equation. To do that, we will be simply solving, Okay, so I wrote down the question and now let's get to solving it. So we have to graph the following function. So what we need to find is the a, b, c, and d values, which are given to us here. So a is equals to 2, b is equals to 7, c is equals to 4, and d is equals to negative 1. Now, using the 4 equations we learned today, we could find all the key information. For example, the vertical asymptote, would equal to, or can be found by making the denominator equal to 0. So for x minus 1 is equals to 0. So for x is equals to 1, x is equals to 1 over 4. This is our vertical asymptote. Now, the horizontal asymptote is equals to the values of a over c. So that is equals to 2x plus 7 as then that divided by x. All you have to do, or what I like to do, is just say y is equals to a over c. So y is equals to 2 over 4. Y is equals to 1/2. That's our horizontal asymptote. Now our x-intercept is equals to when the numerator is equals to 0. So we have 2x plus 7 is equals to 0. So 2x is equals to negative 7. X is equals to negative 3.5. Honestly, I'm not sure whether or not you guys mind the fact that I write fractions and then also in decimal points. It just makes my life easier to just visualize it, because whenever I divide something by 2, I really don't like to write fraction. But again, just make sure your teacher doesn't mind or approves of it, because they sometimes are really picky about the way you write things. Lastly, we have our y-intercept, which was our b over d value. So what we get is that the y-intercept is equals to y. So, sorry, I would just say it is equal to... sorry, my keyboard just gave up on me. Maybe because I disconnected it to actually write on this pad, but that's okay. So what we have is y is equals to b over d. So what we have is y is equals to 7 over negative 1, which is y is equals to negative 7. With that in mind, we could finally create our graph. So for example, let's insert the x and y plane. Make sure to label them, because again, teachers are very picky about this and also makes your life easier. What we know for a fact is that we have a vertical asymptote at a quarter. So let's say that this is like 1, this is 2, this is 3, negative 1, negative 2, negative 3. We have a horizontal asymptote at 1/2. So again, I'm just gonna make the same kind of grid pattern. This is not the most accurate graph, because again, I'm not gonna use an actual piece of paper to show you it, since it will take a lot more time and it's actually gonna look worse with the camera quality. So this is our only way. Make sure your lines are actually straight and you're labeling straight. I also don't have something like this where it overlaps, because it's really difficult to read, but I can't redo it or it'll take too much time. So now let's graph our key information. First of all, I'd recommend using a different color for your asymptotes. So we have a vertical asymptote at a quarter. Make sure you actually say that it's the vertical asymptote and label it. Then we have a horizontal asymptote at 1/2. Okay, well that wasn't the straightest line I've had, but this is again y is equals to 0.5. Now, I would recommend using another color for your x and y intercepts. The y-intercept is negative 7, which is way away from my graph. This is so sad. I'll just say it's over there somewhere. Again, make sure you plan these things out, but I'm just showing you the general solution. And then our x-intercept is 3.5. Come on. There you go. That's our x-intercept. Now, the idea is this. How are we gonna actually graph these? We know that we have something in quadrant 3, right? And it can't cross this line and it can't cross this line. So the only logical solution is for us to graph the function in the following manner. So we go through the x-intercept, and then we keep going downwards and get until we pass the y-intercept, and then we continue going downwards into negative infinity, and this is negative infinity as well. Again, it's most likely going to be a lot more curved in like this, but my graph isn't the best, so we're not going to talk about it. Over here, as you said, it should be equidistant from your other point. So this is where they intersect. So the distance between this point over here to here, and essentially the point through here to here, should be the same. It's not the same on my graph, because I didn't draw this perfectly to scale, but this is an easy way to check for you at home whether or not you did it right or not. But overall, this is the process you'll be going through. Just make sure you actually have a graph that's following the proper, how would I say it, design features it should have, rather than freestyling it like I am. But yeah, overall, if you get something along these shapes with these x-intercepts and these y-intercepts, these horizontal and vertical asymptotes, your graph should be correct. Just make it a lot more visually appealing. Now let's move on to question 2. Okay, so I once again inserted the question into notes, and now let's get started. Immediately, we could write down what we know. So we know that the vertical asymptote is when x is equals to 2. The horizontal asymptote is when y is equals to -1. We know that our x-intercept is at -0.667 and 0, and our y-intercept is at 0.333. Okay, so again, the form of our function is the following. A is equals to x plus b over cx plus d. Okay, so let's first of all analyze what these x and y-intercept actually means. The reason why I say that is because quite clearly we should know that 0.667 and 0.333 are actual part of a fraction, right? So this is actually -2/3 0, and this is actually 0 and then 1/3. So actually, I don't know if you realize this or not, this makes our life a whole lot easier. So for example, let's analyze the x-intercept, right? So what we know is the x-intercept is it's found by making the numerator equal to 0. And we also know that the equation for it is -b over a. Now, since we actually know what x equals to, we could say that 2 is equals to -b, or sorry, not 2, it should be 0.6. So -2/3 is equals to -b over a. Now that we have two negatives, you could just simply cross them out, and we can find, just by making these two equations equal each other, we find that 2 is equals to b, and then 3 is equals to a. However, there's a very big concept that we have to remember, is that either one of these could be multiplied by the same factor, or the same number, right? So for example, if we multiplied all of these by 2, we would have b is equals to 4 and a is equals to 3. That would still keep the fraction equal to each other, because 4 over 6 is the same as 2 over 3. That's just something we need to keep in the back of our head when we're solving the rest of these. So let's go to another one of the values that we know. For example, we know that the we know that the horizontal asymptote is equal to y over 1 over y is equals to -1, sorry. We also know that it is found by making y equal to a over c. We know what a is equals to, so we could simply find what c is equals to. So now we say that the vertical asymptote, or the horizontal asymptote, is equals to 3 over c. So c is equals to -3. Again, we need to keep in mind that this could be a factor, but it should always be the negative of the a value. That's what we know for sure. And these relation 2 to 3 should always stick between b and a. Now, we could move on to something that has c and another unknown, which for example could be our vertical asymptote. So our vertical asymptote is found by making the denominator equal to 0. So what we know is that cx plus d equals to 0. So x is equals to negative d over c. Again, we know what x equals to, so 2 is equals to negative d over c. C is equals to negative 3. So 2 is equals to negative d over negative 3, which would be the same as d over 3. So we know that we could just cross multiply and get the negative 6 is equals to negative d. So 6 is equals to d. Again, keep in mind that these should all be could easily be multiplied by another number, again starting from this base. But here we essentially found a, b, c, and d. So now we could just do a simple check for the last value that we have, right? This value is our y-intercept. Our y-intercept is simply found by having the values of b over d. We know that b over d has to equal to 1/3. So our b value is equals to 2, and our d value is equals to 6, which again is equals to 1/3. Therefore, we did this correctly. Now we could just write f of x is equals to our values that we found, so 3x plus 2 over negative 3x plus 6. That is the steps you should be taking to try and solve your equations. Again, make sure you actually perform the check, and because that is what makes this whole thing work. Otherwise, you might be able to find another equation that has a different y-intercept, hence it wouldn't be the equation for this graph. Now that we finished that, we could talk about oblique asymptotes, which you probably haven't heard of before. So essentially, when you're dealing with rational functions, so far we've only been dealing with a constant over a rational function, or like in a polynomial function, a polynomial function of the same degree over a polynomial function of the same degree. But now it's really important for you to learn that you could have a polynomial function of a higher power or a higher degree dividing over something that has a lower degree. So for those situations, you will actually have an oblique / slanted asymptote rather than a horizontal asymptote. To find the equation for the OA, or the oblique asymptote, you will need to perform long division. So hopefully you didn't forget how to do that, because what you'll be doing is dividing the numerator by the denominator. That kind of makes sense, you know, that's the whole point of a rational function. You're dividing something by another function. However, in this case, we don't care about the remainder. We just kind of let it hang out by itself and we don't care. The only thing that you care about is actually the quotient. The quotient is actually the equation for the oblique asymptote that you will find. So for example, I graphed the function 3x squared plus 2 and divided it by negative 3 over negative 3x plus 6. So in this scenario, we get the oblique asymptote is equals to negative x plus minus 2. Again, just perform simple long division for this function and you will find that is equals to the quotient. So when we graph this function, it will look as the following. We have our first branch and we have our second branch. The asymptotes are still being followed. For example, here we're reaching positive infinity as x approaches to 2, and here approaches negative infinity equals to 2. But this slant is actually approaching the graph of y is equals to negative x minus 2. It's a linear function, so you should be easily familiar with how to graph one of them to form the asymptote, and then simply again just make the graph come as close as possible to the actual function but never actually touch it. That is essentially all you have to know about oblique asymptotes. If I'm not wrong, and when I was taking advanced functions, the only questions about oblique asymptotes was how you can actually find them. So again, performing long division, but there wasn't a lot of questions actually in for applications of them. As far as I recall, it was more into calculus that you actually start focusing on these things. So don't be too worried about it. Just remember to find the equation for an oblique asymptote. You're simply just dividing the numerator by the denominator and finding the quotient. Also, when you have an oblique asymptote, you will not have a horizontal asymptote. Those are the two key points you need to remember. So lastly for today, we have the following homework. It's not a lot of questions because all of the simple questions can actually be solved using the 4 equations I showed you. Again, you have to make sure that your teacher is fine with you using them, but my teacher personally taught me about them, so I don't think it's going to be a problem for you. Otherwise, let's get on with the homework. I'll just be simply showing you the tutorials on how to do them rather than solve them once again. Okay, so now let's look at the homework questions. Overall, this chapter just focuses on understanding the form of the function once again. Nothing special here. So question 1 and 2 just simply ask you for the vertical asymptote and the horizontal asymptote plus the domain and range. Nothing difficult. Apply the equations I showed you today. That is why I didn't assign them. I assigned question 3 though, which asks you to sketch each function and summarize its increasing and decreasing intervals. So A, C, and E are the ones that I assigned to you. For each of them, again, you could apply the 4 equations I showed you. So you first find your vertical asymptote, your horizontal asymptote, your y and x intercepts. Then, when we're talking about the increasing, decreasing intervals, what you need to again remember is that graph I showed you in question 3 in chapter 3.1, where it's like, oh, if you're going from the negative infinity to your vertical asymptote and the graph is approaching negative infinity, then that means your slope is actually negative and your function is decreasing. Those are the kind of things you need to remember. Again, just that graph. Overall, these types of graphs actually look really similar. So for example here, this is what I just described. We're going from negative infinity to our vertical asymptote, so our line looks like this, which has a negative slope. It's also decreasing because, as you can see here, the values as the graph approaches the vertical asymptote from the left actually decrease. And over here we have again a negative slope, just because we're going from high numbers to low numbers. But as the values approach the vertical asymptote, the values are actually increasing. So that's all you have to understand. Summarizing this idea would be done in a table like what I showed you in last class. But again, it's nothing difficult, so I believe you got this. I also sent question 4, which asks the following. For the function f of x is equals to 2x divided by x minus 3, compare the slopes of the tangents. Okay, so what we're actually getting over here is applying the knowledge we got in chapter 1 about rates of change. Once again, this will be a common theme throughout the whole textbook, at least for everything that has algebra in it. So that's everything. But yeah, all you'll be doing is applying the formula you've learned, which was delta y over delta x. And with that in mind, you're also going to be using values that are very, very close to 3.5, because that's what a tangent means. With that being the case, what you should get for 1, so A1, is that when the slope of the tangent at x is equals to 3.5 is negative 24, and that at x equals to 20, the slope is negative 0.02. So it's drastically bigger. Now for 2, again, plug in the values, find y, then find delta y over delta x, and you will find that the slope for 2.5 is again around -24. And then for x is equals to -20, the slope will now be -0.01. Next, it's asking you to asking what these results indicate about the key features of the graph. So if our slope, for example, from 3.5 to 20, it actually became less and less steep. So it was increasing, right? And then as x was smaller than 3, it was actually decreasing. So let's graph that and I'll show it to you why that is. Give me a second. 2x divided by x minus 3. Okay, so what we have here is our vertical asymptote right there. Over here, we're talking about whether or not it is increasing or decreasing by finding the tangent. So at 3.5, we found out that it was around 24. It's x equals to 3.5. It's 14. So what we're doing is again just getting really close values. So for example, with that, so that value minus 14 divided by that value minus 3.15, and you'll get your answer. But we also see that since when we're coming closer to the vertical asymptote, the function is actually increasing. Now looking at this, as we're getting closer and closer to the vertical asymptote, the function is now decreasing. That's simply all you're finding out. Now I've also assigned question 7. So write an equation for the rational function shown on each graph. Okay, so all you'll be doing is again using the 4 equations I showed you. And over here we know that the vertical asymptote is equals to 3, the horizontal asymptote is equals to 2. There we have our x-intercept and our y-intercept. So you could follow the exact same steps we had before. Again, remember that 1.5 is the same as 3/2, which could make your life a whole lot easier. Just a little tip. For b, we have our vertical asymptote is equals to -1, our horizontal asymptote is equals to 1, x-intercept is 4, and y-intercept is -4. So here you might actually have to start dealing with some factors of these. For example, if our x-intercept if our x-intercept is 4, so the top value should be x minus 4, right? But it could also be, for example, 2x minus 8, which would still give us as an x equals to 4, but now we have different a and b values. So that's the kind of things you need to look out for. For that reason, you should always do your check, and if your check doesn't come out as the same value, figure out by what factor you must multiply the last value that you found to get the right answer, and then just simply multiply everything by that to find the actual A, B, C, and D values. So it'll be a little bit like guess and check, but not really, considering the fact you should be able to simply figure out by what factor you should multiply everything by. Okay, I've also assigned question 9, which makes you write an equation for a rational function, which has the following things. This is genuinely the exact same thing as using the graph, but now you're just immediately given the values. So over here, again, we have the x-intercept with 3/5. That makes your life really easy, because for example, you could say that 5x minus 3 could be or plus 3. No, it should be minus 3. 5x minus 3 could be your numerator. From there on, since you found your a and b values, you could now substitute those into either the horizontal asymptote or into the y-intercept, and then solve for the next value, and go so on and so forth with your happy merry life. Lastly, I've assigned 13, which is an achievement check. I usually don't like assigning these because the textbooks never have answers for them. But essentially here, we just have to consider the following function, find its vertical asymptote domain, horizontal asymptote and range, and sketch the function, summarize the increasing and decreasing intervals, and then compare the slopes of the tangent. Again, the only complicated part might be part G, but all you're doing here is again just finding those key values and then saying, oh yes, it is increasing or decreasing, or the tangents changed by this much, therefore it proves the fact that the function was increasing or decreasing. With that in mind, that's it for the homework today. You could do all the other questions, but they should be really repetitive, which should give you a lot of practice. But again, if you don't want to do them, you do not have to, unless your teacher assigns them to you when school is back, even though it's online learning. So yeah, overall, today's lesson was probably one of my favorite lessons out of chapter 1 to 3, just because of the implications and the wonderful 4 formulas you could find. It makes your graphing life so much easier. Also, finding out the equations for the graphs might seem intimidating at first, but honestly it's like a little riddle that you're always solving. Or like, you know, those crosswords where it's like, oh, find what this actually means, or like, what is the most famous like football player. Yeah, it is just a really fun activity where you almost forget that you're actually doing math, personally for me. But with that being the case, we have only chapter 3.4 and 3.5 left. Chapter 3.4 is more inequalities, so that should be fun. In chapter 3.5, this is essentially just applications of everything we learned thus far. So for that chapter, I think I might just go over everything in a large summary rather than try to show you how to solve different variations of word problems considering rational functions, because I feel like that would be extremely unbeneficial for you, since the only way you're going to learn is by actually doing them yourself. Well, with that out the way, I hope you had a lot of fun listening to today's class. I know it's probably something really new that you haven't experienced before, considering we have learned about oblique asymptotes. But again, if you have any questions, feel free to contact me in any way you feel is good enough for you. Otherwise, I can't wait to see you in my next lesson. Goodbye!